Hey guys, this is the Great Fez. I am back with my final video on my Ascent algorithm evolution. Uh, First, let me apologize. It's been so long since the last video I made, and it's just been a crazy couple months. Um, so to touch base on um, what we did before was we had a square root ascent function. So we hard coded a square root function that had um, some values that I tuned from data collecting. But the problem that this was having is that I actually had to tune these values, right? These values had to change based on each of the ship's parameters. And so what I wanted to do is create something that it essentially auto-tuned itself, and I didn't have to really mess around with any of the values. I didn't have to morph the trajectory. The trajectory um, would be controlled by the ship's parameters. So the action items that I wrote, I think these are probably a little different. I've changed some of them, but the first one is to switch to using lexicons for integration. A lexicon, I'll touch base what it is in a second, but essentially it just cleans up the code so I don't have this big list of calculating, time one, time two, the acceleration, the integrating stuff. I'm able to put all of that into a function, and I can use lexicons to transfer the data that I need to be storing and saving over and over. Second part is the main important one that we're going to be definitely going over a lot of is the new system for pitch rate control. So before it was just a hard-coded um, in, square root function, and now we're going to be calculating the pitch based on where the ship is relative to where we want it to be and um, its performance or the acceleration. And then the last part is implementing this Azimuth calculator. It should be an instantaneous Azimuth calculator, and I'll go over that a little bit. I'll show you guys the code, but I'll point you to where the actual math is derived. I don't want to really go over too much. It's a pretty understood equation and functionality. So lexicons, just to touch base, if you're familiar with Python or if you're familiar with MATLAB, Python has dictionaries, MATLAB has structures, but they're all kind of the same thing. Lexicons are a way that you can give a variable a lot of different data, and you could store all kinds of data in there, and so that way you just have one variable, um, and then within it you can have other multiple variables, and they could store lists, values, and all that kind of stuff, and it's kind of organized and gives the lexicon properties that you can pull. So it just kind of cleans up the code a lot, and I'll show you how the code is cleaned up in a bit. So to jump right into the pitch rate control, the thing that I wanted to go over first is what the goals are, right? So with any guidance scheme, you have 2 points, right? You have where you start and where you want to end. In this case, for all these cases, we've started at the launch pad, 90 degrees pitch pointed up, and then we want to end it at we want to end the pitch over at 5 degrees pitch and 70% of the atmosphere altitude. So why 70%? Well, this is an arbitrary value that I chose just for testing, but it seems to work really, really well, and so I just decided to keep it. There's no, I'm sure I could maybe tune this or something, or make it better so it works across a bunch of other ships, but or should I say that it works best for all ships, but I didn't see any need, and I never ran into any issues with this number, so I just kept it. But this assures that I'm way above the atmosphere, the thicker part of the atmosphere, and then a percentage just means it scales to other planets. The degrees part, however, I chose this because 5 degrees is about roughly 99% of the thrust. So you're still going to be using most of your thrust, I mean 99% of it. You're still going to be accelerating horizontally, which is the important part. But with 5 degrees pitched up, you still have that little bit of vertical acceleration. So that means that I'm still trying to, I want to get out of the atmosphere, not just out of the thicker atmosphere. I just want to get out of the atmosphere entirely quicker. So with still a little bit of vertical acceleration, I can get there quicker. All right, so I color coded this, and I apologize if it's hard to read, but um, the hopefully the colors help. So This is essentially the algorithm that it goes through. There's barely any math here, and I didn't want to type out the entire quadratic formula here, but so to go into it, the inputs are the vertical speed, the vertical acceleration, current pitch, and altitude. So if we started out from zero, our vertical speed is zero. If the engines are ignited, then let's say you have a vertical acceleration of 1.1 thrust to weight ratio, so about zero point 0.1 Gs or something like that. The current pitch is 90, and then the altitude is, for all intents and purposes, zero. So the final altitude is just a calculated variable that you put in the atmosphere height, and so for carbon is 49 kilometers. Final pitch is 5 degrees. The altitude difference is the difference between your current altitude and the final altitude. And then the time to final altitude. Now, if you've ever seen the like a constant acceleration equation, you put in the current speed, the acceleration, and then the altitude, and then you can, using the quadratic formula, you can solve for the time that it would take for whatever it is that's, it could be a rock or a rocket or whatever. Assuming a constant acceleration, you can calculate the time to the final altitude. Now with that, then we calculate the constant pitch rate that will get us to 5 degrees from 90 in this time, right? And so every time that this is calculated, we get this pitch rate, and then we add it to our current run. So this would actually be a negative value, right? Because 5 degrees is less than 90. And so every time we add it, our pitch is going to decrease um, and iterate or integrate over time. So every time step, we're going to be getting a new pitch. And this time to final altitude will start to decrease the closer we are, right? But also start to decrease the faster we're going vertically and the faster we're accelerating vertically. But the cool thing is that it starts to taper off as we start to pitch over because the vertical acceleration starts to go down, and we might even start decelerating, and the vertical speed might actually start dropping down. So it kind of levels off on itself. So at the beginning we're gonna have slow pitch over because we want to get some vertical speed and get out of the atmosphere. Then in the middle of the flight, we're going to be pitching over pretty quickly, and then towards the end, we're going to be tapering off. So that's how the functionality works, um, and I'll show you guys the code and how that's done. It's really just copying over that formula there. The Azimuth Calculator. So this is something that I wanted to implement because now I'll have a total control over the launch. Whenever all the previous ones that I've been doing has just been on equator, so the inclination that we're trying to target is zero. However, if you want to target something greater than zero, or any inclination, you have to launch uh, at a heading that isn't 90 or directly east or west, right? And to do that, to calculate it, you use some vector math to determine. Here, I can pull up the vector math. This points you to the Orbiter wiki. I know it's Orbiter. I know it's not KSP. Don't harp on me, but it has this fantastic diagram here. So if we were right here at the what's it called, at the launch site, Earth is rotating. In this case, it would be Kerbin, but Earth is rotating to the east at 408 kilometers or meters per second, and then we want to be at 7.7 kilometers per second. So that's the orbital speed at this 45-degree angle. So you can see that if we burn in this third vector direction constantly, we'll accelerate ourselves all the way up until the 7.7 kilometers per second, and our inclination will be 45 degrees. So this vector right here is the calculated heading that we need to point to. Our ship needs to point along this vector. So that's how that is calculated there. And then the equations and stuff are in that orbiter one, and you guys can go through that. And then I also have the code here. So presenting version 3 of the pitch rate control method. This is the final version of my Ascent algorithms thus far. I don't really have any plans to improve this. It's working pretty well. So we've updated it to have a pitch program is not controlled by pitch rate. Azimuth Calculator is in there, and then all our integration is done with Lexicons. So with that, let me pull up. So first, let me show you where I'm going from this. So I have 2 commits from since my last one. The pitch rate control is here. So what this is going to show you is just the differences between the two. And so green is new and red is uh, deleted or changed. So I left in the pitch program square root function in here. I changed it from pitch program to pitch program square root, and then I added this pitch program rate. Before I touch this, I actually wanted to show you the lexicons. That way, I'm not going back and forth. So here's an example right here of a lexicon. We have set pitch data to lexicon. Then I add time, the key time, and then I give it the time in seconds. So now if I wanted to call that data, I just say pitch data, where is it? Pitch data time, and then I can set that variable. I can pull that variable, like right here. The pitch desired is pitch data to pitch. So right here, I'm pulling that key and getting the value that it's stored in there, and then setting it to here. And at the end of the day, um, all I do is just return this pitch data lexicon. So the input is the pitch data, and the output is the same pitch data. So I'm taking all this initial data, putting it through the iterator, and then spitting out the new data. So every time just gets updated every time it's called. The time in seconds stores when it was last called, so I don't have to put any I just have one wait for the entire function, because every time that this gets called is going to be reading the time whenever it's called, so I don't have to, iterate twice or every other time. So I did that with the pitch data, which is for the what's it called, for the pitch rate controller, and then I also did it with the delta V. So I added here the calculate delta V function. So again, you just put in the lexicon that's delta V data, and then it returns the delta V data here, and then it just iterates every single time. So that's that here. The other thing I added, just something quick, is I changed the look direction, or I changed this heading to look direction, and then set it to the ship facing up vector, which means this is just a fancy shortcut so that I don't care about roll anymore. The ship is going to maintain the roll. Like it's not going to try and turn to face the ship in any direction. When it launches, it just goes straight into the pitch over. Um, change some of the code here to more align with the pitch program rate, and then you can see here how clean this code is. I've taken all of this code out for the delta V calculation and just set it here. Now I just calculate delta V, give that delta V data, and then it outputs this, and then I iterate over and over. And then you can see here, to get the total data, I just use this the lexicon. So I call the total key, and it prints that out. I call the gain. I can subtract them, divide them. It's just they're all just values. Um, that's all the code that I've done here for pitch data, and then the delta V data, and then the next commit. So that was this one here, and the next commit I added the instantaneous. I also changed it to version 3 here. Changed this orbit to 250,000, and you'll see why in a second. I added this, or I deleted declare because I wanted to clean that up. And then here's the instantaneous calculator. So give you an idea, right here I have this max function where it calculates the circular velocity, or it uses the ship velocity +1, just because if you go above this value, it'll start telling you you need to point backwards because you're going too fast. So this way it's always trying to accelerate is essentially what it's saying. But yeah, you can just go through this on your own as far as a calculator, but at the end it tells you the compass heading that you need to go in, and you can see that here. So this is the inclination that's desired, so I set it to 10. The compass is now in this equation here, and then this gets calculated every time down here.
set compass to instantaneous azimuth, and then I print out the compass here. So, and then I actually, this used to be action group 1, and I changed it to 3. See why in a second. But I think that's everything that I had for here. Oh, yeah, that's everything I had there. Let's actually go in, show you how it runs. And the reason why I have all those crazy things, because I downloaded the Saturn V off of Steam. It's a fantastic ship that someone made. Um, very, very well made. I removed some stuff. I adjusted it. Obviously, I added some the KOS terminal and put the gravitation meter and the acceleration meter. So, without further ado, let's launch. And you can see here it's accelerating, and then the pitch angle is being calculated constantly. So right now I'm aiming to this pitch here. The compass heading is 79.2, and you can see we're starting to pitch over, which is somewhere around this line here. We're starting to pitch over to hit that compass heading. And our inclination will start to build. So before it was just set to 0. Now we're going to try and hit 10 degrees inclination. And yeah, I mean that's pretty much all it's doing. So every time it's iterating, it's calculating the vertical acceleration. It's taking into account the vertical speed, seeing how long is it going to take for me to get from this point to 449 kilometers, and then pitch over so that I hit that pitch angle at 49 kilometers. So um, as we just watch this go, the other thing I wanted to discuss is a little bit of a surprise to some. I think some people will be pretty excited about this, but I want to redo my total autonomous trip to the moon. I did this before. I made this video a long time ago. I think it was like 3 or 4 years ago. I'd have to actually go look. But it's the first video I ever made on YouTube. And I did it so I can apply to SpaceX. That never panned out. They never responded to me, which is fine. Although, someday I might work for them. Someday I might work for somewhere else. No worries. I'm doing okay for now. But it is a very old video. The code in there is very crude. A lot of it is hand coded. A lot of it is approximations. I want to totally redo it. And this time I want to go to Minmus. And when I go to Minmus, I want to do the full, the Apollo 11 style mission. So, separate here, dock the two, land, uh, rendezvous in Minmus orbit, and then come back all together and land. So that should be really fun. It should, we've already done, or I have already done all the Ascent guidance stuff, so that's pretty much taken care of. And by the way, we're about to hit that 5 degrees here, and you can see that we're getting pretty close to 49 kilometers. Boom, 85 degrees, 49 kilometers. So that's what I wanted to do, right? I wanted to pitch over at 85 degrees or 5 degrees pitched up when we hit that 49 kilometers. So that worked out pretty well. And you can actually see the inclinations starting to, it tapers off because the velocities start to align, and so the differences isn't very big, but it's getting there. You'll see that it actually gets to within very, very close to the times that I've been looking at it. So anyway, back to what I wanted to say. Yeah, it's just the things that it touches on is ascent. I can talk about orbital maneuvers. I can talk about rendezvous. I can talk about transferring to other bodies. I already have my landing code, so I can just implement that. I can talk about docking, automate all of that. I want to go step by step through the entire mission and just automate the whole thing. I think it'll be a very, very fun project to do, and I can make videos of that, and then maybe just one at the end to just show the entire thing, um, just go autonomously, and I think that'd be pretty fun. So that's my next project, and I just want to wait here until this is finished running. It should be pretty close. The other reason why the reason why I set this to 250,000 instead of 150 is because at roughly 100 or 150, I was
barely had any fuel left, and I didn't like that. So I want to just burn up the rest of this fuel so I can get into the next stage and not have to worry about it. So here we'll probably cut off, and yeah, there we go. All the stages. There we go. And now close it out. And if you check here, look how close that is. Inclination of 0.00016. So it worked out pretty well. This total V for circularization, I think it's pretty decent for what it is, and we are going to a little bit of higher orbit. So if you wanted to take that for comparison to my other stuff. Well, that's pretty much it. Hope it made sense. Same as always, I'll put the code in the comments. You guys have my presentation here. This will be the last Ascent video, unless I come up with some crazy idea, but that'll be different time. Until next time, hopefully I'll get my project going with the Apollo style mission, and see you then if you come back. Thanks.